This is 3.5, day 1, where we are solving exponential and logarithmic functions with word problems. This first slide, I don't want you to write anything down. I just want to talk about it just so you can recognize the difference between the two graphs. When you talk about exponential growth model, think about it as a problem where you have a penny. Tomorrow I give you 2 pennies. The next day I give you 4 pennies. The next day I give you 8 pennies. That's a doubling amount. It's going to start to increase over time. So it looks like that. An example of a decay problem would be something like we have bacteria. And over time that bacteria reduces in size. The person's getting healthier over time. So it's going to decrease in value. So over time it'll decrease. So that's what the 2 graphs would look like. So you'll see some word problems today where they'll introduce those words to you, exponential growth or exponential decay. This slide I would recommend that you write down. It's very similar to PERT, that compounded continuously when we talk about money earlier this chapter, where Y is the end amount, C is the initial amount, the original amount. The E is that E that you've known all chapter now is approximately 2.71. You use your calculator for that. K is always in decimal form. If your K is greater than 0, you're going to have a growth rate. If your K is less than 0, you're going to have a decay rate. It's going to decrease over time. And then your T is your time. I'll give you some time to write down that slide. All right, this word problem is lengthy. I'm going to highlight what I do want you to write down. You don't have to write down the whole paragraph. So what I want you to write down is this formula. P equals 5,340 E raised to the 0.01292 T. And what this formula represents is they tracked the world's population from 1995 to 2003, so for over 8 years. And they come up with the growth rate. It increases over time, and that's the formula. And then it says the end amount, P is a population in millions. The T equaling 5 represents 1995. According to this model, when will the population reach 6.8 billion? So this P, this value right now, 5,340, is in millions. So we're going to work through this problem. So again, what I want you to have written down so far is the equation, the formula. So we're going to let t equals 5 is 1995. And we're going to refer back to that later. So we're writing that down, that information. When the t equals 5 in this formula, we're at 1995. And then we're given another information that when will the population be 6.8 billion? So what time, the time is unknown, when will the population be 6.8 billion? So that's what we're trying to find, the time. And unfortunately, we can't go right into substituting into the equation. Why can't we? What are the different units that are going on, that are given? Billions and millions. So we have to convert one or the other. So if I want to convert this given 6.8 billion into millions, what do I do? How do I convert this 6.8 billion to millions? What is it? Times it by 1,000, great. So times it by 1,000, we can just move that decimal 3 places to the right. So we have 6,800 million is our given. So that's our end amount. So we want to go out and find out when would that actually happen in the future. So let's go ahead and substitute it in now into the formula. So where is that 6,800 going to go? On the left side, do you agree? Okay. So we use this formula right here. 6,800 is our end amount of the population. That's your initial amount, 5,340 million. And then E raised to the, don't worry, this decimal place, not all of your homework questions will be this long. So now think back to the last few days when we solve equations. What are we solving for? T. So think back to 3.4 lessons. How do we solve that equation for T? Before we can ln it though. Good. Divide it first. So 5,340. Yep. So 6,800 divided by 5,340 equals E raised to the 0.012922T. So then with your calculator, let's reduce down that fraction. So we get approximately 1.2734. All right, then we have that isolated E by itself on the right. So we learned about that we can remove that E by doing what? Natural log it, take the inverse of it. So I have to do both sides. The natural log of 1.2734 equals the natural log of E to that exponent. So what is going to happen to that right side? It's going to cancel out, and we're left with just that decimal. And it's not an exponent anymore. The natural log and the inverse will cancel out. The left side stays as it is. What's my last step then?
Divide by that decimal.
Yep, divide by that decimal. So now my t is alone.
118.4.
So t is approximately 18.7 years. Am I done with the question? I'll let you finish writing that up, and then we'll go back up to the slide. It says t equals 5 represents 1995. And our t equals 18.7. So let's go backwards a little bit. When is t equaling 0? When would t equal 0, time equal 0?
2000.
1990, we'd go back 5 years. So 1990. So now my t equals 18.7. So how do you find out the time? I would start with this, 1990, and I would do what? At 18.7 years.
2008.
So when t equals 0, that was 1990, and we had time equaling 18.7 years, so we want to add those, 1990 plus 18 more years.
2008.
Yeah. In the year 2008 is our answer. In about a half a year, about 6-7 months. So in 2008, our population will be at that 6.8 billion. We could go out and check if we want to check the census and see if that truly was the growth model that was happening. Maybe it was more.
What is that decimal?
The decimal is the growth rate. So they went out and calculated already, some mathematicians went out and calculated it, and they got the growth rate here for those 8 years. They watched it and saw the pattern and figured out the percentage. Because this is the percentage. It was about increasing about 1.2%. Okay, let's go on to a new style question. Let me stop the recording there.